You know that incredible moment in a cricket match when the batsman just connects perfectly and the ball sails into the crowd for a six? It looks like it's all about raw power and timing, right? And, well, yeah, it is, but it's also a seriously cool high-speed physics problem. So today, we're going to peel back the curtain and look at the hidden science behind that perfect shot. We're talking about the invisible forces that make all the difference. All right, let's get into it.
So there's this idea floating around, almost like a secret, that all cricket players should know this one specific formula for projectile motion. And you know what? It's kind of true. There is a formula that, on paper, is supposed to explain exactly how that ball flies. A lot of us probably even saw it in a high school physics class. But here's the catch. It only tells you about half of the real story.
And here it is, the textbook classic. This is your standard projectile motion equation. It's designed to describe the path of something, say a cricket ball, but only in a perfect theoretical world, like in a vacuum. You just plug in the angle, the speed it leaves the bat, gravity, the whole shebang, and boom, you get this perfect, clean arc. Yeah, so in this perfect little bubble, this textbook vacuum, the ball flies up and comes down in this gorgeous symmetrical curve called the parabola. The trip up is a literal mirror image of the trip down. It's neat, it's predictable. And on a real cricket pitch, it's totally, completely wrong. Right? Because the real world is messy. It's not a vacuum. You've got wind, humidity, and the big one, you've got air. So what actually happens when this clean, perfect formula has to face the reality of an actual cricket field?
Well, everything changes, and it's because of one single invisible force that's a total game changer. Air drag. You might know it as air resistance. This is the one thing that separates the physics textbook from the cricket stadium.
So what is air drag? Well, it's pretty much what it sounds like. As that ball is rocketing through the sky, the air is constantly pushing back on it, acting like a brake. It's this relentless force that's slowing the ball down every single nanosecond it's flying.
Okay, so let's put these two things head to head. We've got the perfect world of textbook physics on one side and the real world, where air drag rules everything, on the other. A little showdown, if you will.
So the big question is, how much of a difference are we really talking about here? Is it a tiny little tweak, or does it completely change the physics of the game? Let's find out.
Whoa! Okay, now this image shows you everything. That smooth, solid line, that's our perfect little textbook dream. But the dashed line, that's reality. Look at it. It's shorter, it comes down way steeper, and it's not symmetrical, not even close.
Let's break that down. In that no-drag world, the path is perfectly symmetrical. But with drag, it gets all lopsided. And here's why, and this is super interesting. The air is constantly slowing the ball down, right? So it's losing forward momentum the whole time. This means it actually travels further horizontally on its way up when it's moving fastest than it does on its way down. Crazy, huh?
And if you want to see the effect on pure distance, just look at these numbers. It's staggering. Okay, so you hit the ball at the same speed, same angle. In a perfect vacuum, that ball is flying a whopping 160 meters. But in the real world, with air drag, it only goes about 90 meters. Air drag literally chops the distance of a monster hit, almost in half. That's insane.
But wait, it gets even weirder. Air drag does something else, something kind of counterintuitive. It basically creates a physical speed limit in the game. It's what economists would call a law of diminishing returns for guys who just try to hit the ball as hard as possible.
See, in that simple textbook world, if you hit it harder, it goes further. Simple. But in the real world, it's not that easy. The faster you make the ball go, the harder the air pushes back against it. The drag force gets stronger and stronger with speed.
And this graph is the perfect way to see it. It's showing you the flight paths for hits at different speeds. Now look at where they land. See how at the lower speeds, adding a bit more power gives you a nice big jump in distance? But then look at the higher speeds. The landing spots start to get all bunched up.
Let's put some numbers on it. Let's say you increase your hit speed from 80 to 100 meters per second. That's a 20 meters per second boost. For that, you get about an extra 20 meters of distance. Okay, not bad. A pretty good deal.
But now, check this out. You add the exact same 20 meters per second of speed, but this time, you're going from 100 to 120. And what do you get? Only about 10 extra meters. You put in the exact same extra effort, but you get half the reward. That is the law of diminishing returns, right there on the cricket field.
So not only does air drag steal distance and punish pure power, it's got one more surprise for us. Remember that perfect 45-degree angle we all learned about in school for getting the most distance? Well, yeah, air drag messes with that too.
Yep,
Turns out 45 degrees isn't the magic number in the real world. Because of air drag, you actually want to spend a little less time flying through the air, giving it a chance to slow you down. So the best angle, the one that gets you the most distance, is actually lower. For a really powerful hit, it's something closer to 37 degrees.
So we've got all this physics setting the rules of the game. But at the end of the day, it takes a truly incredible athlete to actually play by and beat those rules. So let's look at the human side of this. What does a batsman actually have to do to make all this happen?
Think about it this way. When a batsman hits a six, they aren't just swinging a piece of wood. They are solving an incredibly complex physics problem instinctively in the blink of an eye. They're calculating speed, trajectory, timing, all to beat gravity and air drag.
And how fast do they have to do it? Well, against a fast bowler throwing at 140 kilometers per hour, the batsman has less than half a second. That's it. From the ball leaving the bowler's hand to it reaching them, they have 0.46 seconds to see it, judge it, decide what to do, and get their body in motion.
And in that tiny sliver of time, they have to get their bat moving. And I mean moving. From a dead stop, they have to swing it to a speed of about 19 meters per second. That's roughly 70 kilometers per hour, just to connect with the ball with enough power.
Getting the bat up to that speed, that quickly, requires an absolutely mind-blowing amount of acceleration. We're talking about 4 Gs. That's 4 times the force of gravity. It's the kind of G-force that fighter pilots have to train to endure. It is just a purely explosive, amazing feat of athleticism.
So there you have it. The next time you're watching a match and you see that ball fly into the stands, remember what's really going on. It's not just a batter against a bowler. It's an athlete in a split-second battle against the fundamental laws of physics. And it really makes you wonder, doesn't it? What other amazing scientific secrets are hiding in plain sight in the sports we all love to watch?